What we would like to do is talk about the thorium cycle as an innovation. We heard the word innovation 3 times already on the economic section as a way of reintroducing new ideas in terms of the industrial, of course, and the scientific realm. Along this concept, Bill Gates himself made the remark that nuclear energy has not seen much really new innovation. It was suggested to him the concept of what's called the traveling wave reactor used on the plutonium cycle. Engineers started looking at the problem, how to cool it, how to extract the energy, and they ended up basically with the fast reactor system. So in a way, they have reached some kind of a dead end. Here still we have a new line of innovation. Many people have contributed to it in the past, starting from Edward Teller and many of the prominent people here present at different laboratories, Argonne National Lab. I contributed to it at Oak Ridge National Lab. Of course, Livermore also should be recognized. What we are talking about here is a particular aspect of the thorium cycle. Thorium has a single isotope in nature. It has only the thorium-232 isotope. So you cannot build a critical system based on an isotope that has an even number, an even mass number, 232. You can build it with the plutonium-uranium cycle because you can start it with uranium-235, which is an odd number, of course, mass number isotope. So if you want to start the thorium fuel cycle, you need some kind of a spark. The spark come in by starting the cycle initially with either uranium-235 or plutonium-239 as fissile isotopes, or another approach is to provide a source of neutrons. And of course, our gentleman from Fermilab here could tell us that, oh, we can use particle accelerators to provide that source of neutrons. But you can also provide the source of neutrons from fusion. There are several fusion experiments today that have a problem of not breaking even in energies. This is called the Lawson Criterion. It's that to create the conditions to really get fusion going, like in the stars, thermonuclear weapons, we know it can happen. The energies that you invest into creation, the conditions for fusion, are more than what you end up getting as energy out. Yet, some of the current experiments, in fact, can be used to be that spark as a neutron source for starting really the fusion reactor, a thorium type of a system. That's what we'd like to explore in this talk. What we are going to talk about is 2 particular concepts. One that we have exists, in fact, as an experiment at the University of Illinois. This is an electrostatic confinement fusion system. I'll show you the principle of operation. It uses simply the idea of the diode that you all know about from really high school physics. There is also another concept that was introduced by Robert Bussard that uses cusp magnetic fields. And that's also a favorite of mine because we did some work on cusp magnetic fields some time ago at the University of Illinois also. If you use fusion and fission, now hybrid, a combination of both, you gain the benefits of both fusion and fission at the same time. You benefit fusion in that you can build small experiments that hopefully will develop and the technology will develop that in the future we can have pure fusion, maybe to replace fusion in general. What we have done is that carried out the equivalent for that fusion hybrid of what was called the Lawson Criterion, a British engineer who tried to set up the conditions under which you can have basically energy break even if you have a pure fusion system. Here we tried for a hybrid of fission and fusion. I'll show you only 2 equations. If you want to go and look at the detailed derivations, you go to the paper that I have shown earlier, and if you find typos or errors, please bring them to our attention. We'll correct them right away. We'll show that such a configuration allows energy break-even for a sustainable, very long-term energy system that can last for thousands of years, basically. Thousands of years of energy. And we say it without enlarging it in the same way, probably as Alvin Weinberg said it, it's a practically unlimited fuel supply base. Because if you develop fusion to burn deuterium, deuterium occurs in the ocean's water, basically, at 150 parts per million. So what you would be burning is water and producing out of water energy in general if you associate it with thorium. And of course, we can introduce maybe in the future aneutronic fusion fuel cycles. In that case, use deuterium and helium-3, or like Bussard initially envisioned, using a proton-boron-11 fuel cycle that produces only charged particles, and he considered it maybe as a way of providing propulsion for travel by, of course, humans towards other solar system, maybe in the long term in general. So let me go very quickly about the ideas that are in the full paper and try to fill it within the 30 minutes that we have. I had an interesting question by a gentleman earlier here about the ability of us of breeding, meaning producing more fissile fuel than what we burn in the thorium fuel cycles. And Professor LeBlanc here knows that we can breed with thorium, the thorium cycle, either with neutron energies that are in the thermal region. We call them KT neutrons. They have an energy of 0.025 electron volts, or a speed of 2,200 meters per second. And the criterion here is that eta, or the regeneration factor, should be larger than 2. So you could see that here uranium-233 becomes the best fuel to breed in the thermal region. But look here, it breeds as well as plutonium, or even better also in the fast region. We can use fast reactors, or we can use thermal reactors, as has been built so far at the Oak Ridge National Lab as a pilot plant for breeding with thorium. We'll come to this topic back later on. What we envision is a combination of satellites that would be basically burning uranium-233 that we breed in fusion reactors that we call, of course, the fuel factories, either using the deuterium-tritium fuel cycle. This is the easiest fusion fuel cycle that we can really produce on Earth, or for the long term, and if we develop the technology and we master it, all we will need in that case is deuterium from water, from the ocean, as I'll show you, and thorium-232, which, of course, by itself is fissionable but not fissile. In the case where we use DT fusion, tritium does not occur on Earth as in substantial amounts, so we'd have to use lithium as an input. Lithium is still abundant in the Earth's crust, and in that case, you feed the lithium into the fusion reactor and produce tritium out of it. That tritium would be fed back with the deuterium, again, from the oceans, and thorium-233, and you can produce uranium-233 that you can burn in the fission reactor. Such a separation between the fuel factory and the burners, as we call them here, the fission part, is a very interesting answer to the problem that we hear in each one of those meetings. Oh, proliferation, proliferation, proliferation. Oh, what if you produce uranium-233 and some people start using them as weapons? In that case, of course, the fuel factories can be in the nations that abide to the Non-Proliferation Treaty, and other nations can be provided with reactors that only can be burning that uranium-233 in the same way that we provide fuel, say, at 3 to 5% enrichment for pressurized water reactors. We can provide fuel that's enriched in 3 to 5% enriched in uranium-233. They burn the fuel, they return the fuel, they get more fuel. If they start not abiding by the Non-Proliferation Treaty, of course, they lose their power supply. One of my favorite applications of these ideas in terms of using small, compact reactors as neutron sources is use the cusp configuration, and I'll explain to you the cusp configuration. We used it some time ago in one of the references at the end of the chapter for the design of a fusion reactor that used, in that case, fuel like D-helium-3 fuel, so it was charged particles. And our intention was to take the energy directly and convert it into electricity by turning it into the magnetic field. So how do you produce a cusp magnetic field? The cusp magnetic field is very simple to produce. You simply build what's called an IOPHY bar. You bring a wire and you turn it into the plane of the paper. You turn it around, you exit it from this side, you bring it down again, and you bring it back. Each one of those wires produces a magnetic field. This is a magnetic field against the wire. Of course, that follows the right-hand rule, where if you have a current in the direction of my thumb, you have a magnetic field in the direction of my fingers. And in that case, you produce a cusp magnetic field. This is a linear cusp. And the interesting thing is that the curvature of the magnetic field is positive towards the plasma. And this is the most stable configuration where you can contain a plasma. Existing plasmas, of course, suffer from instabilities because they don't have that type of curvature. They have a different curvature. Came in a gentleman, of course, Robert Bussard, and instead of having a linear cusp like what we have here, he produced a conical cusp. In that case, instead of have one line going this way, coming back, and then going back and coming back, he used simply two rings. One ring on the top, one ring at the bottom. So this is now a ring of current. This is a magnetic field configuration around the ring of current, another ring of current, and you get a cusp magnetic field where a plasma can be confined and become extremely stable in the center right there. He didn't simply stop at building two rings like I've shown in the diagram. He took the idea of the little toy called the wiffle ball, and he simply used three pairs of circular fields. So this is magnetic field by a circular wire here, another here, one on the other side, one on the other side. And he gets a fascinating, very stable in terms of the configuration of the plasma. His work was kept classified for a long time. In fact, our work also on the linear magnetic field was classified, and until now, we don't know why it was classified, because the reason for classification is itself classified. This is what we are told. And notice what he came up as a very interesting, simple design. This is a picture of his device. You can see one coil here, one coil at the bottom, 6 coils, generating a cusp magnetic field in the center where a plasma can be confined very easily. The United States Navy supported his work, and their goal was to build a 100-megawatt thermal reactor that could be maybe used on a nuclear submarine. The initial design that I showed earlier did not work very nicely. There were too many electron losses, and the reason was that he had his coil touching each other. So a new configuration, now you could see here, the coils are just wiring. The plasma would be confined in the center. You create a vacuum center there. And his goal was to burn proton and boron 11. This is a fusion fuel that produces only charged particles, no neutrons, no radiation, no activation of the system itself. And it doesn't have to be proton boron 11 or a hydrogen and boron 11. You could use, as we mentioned earlier, initially a DT plasma. In that case, it becomes a source of neutrons. Or you can use a DD plasma. You also can get a source of neutrons. This is one approach, and I call it an electrodynamic approach. At the University of Illinois, there is work that, an experiment, in fact, that is operating using a different concept that you could call electrostatic confinement. Electrostatic confinement uses a very simple idea of a diode. So all you have to do there is create a grid. You create a positive charge on the outside of a container.
You accelerate the ions towards the grid. They go through the grid, they accumulate near the center, and in that case, you use deuterium, and in that case, you can produce also a source of neutrons. And this experiment is real in that it creates a well that really contains a plasma. Unfortunately, both experiments have what's called the Q value for the plasma that's very low, 0.01, meaning that you produce, you spend 100, say, watts of energy, and the plasma gives you out only 1 watt of energy. So in that case, it is not a power-producing system, but it is a fascinating, really, neutron source. In fact, you could see here one application of it that is being adopted now by NASA, replacing chemical rockets where you would use, of course, a propellant and an oxygenator like oxygen and hydrogen. They are using now thrusters for their really long distance satellite. For instance, you could see here they're using xenon. And if you accelerate the xenon ions, basically you can get what's called an ion thruster, and that's what NASA is using, as well as it's being used as a neutron source. This is a real experiment. These are not really pie in the sky. This is, for instance, a device that has a 2-grid and another one that has a multi-grid diode where the ions are accelerated, concentrated near the center. And if you use deuterium, of course, you get a neutron source. And this could be a neutron source that could be used for as that spark that we say is needed for, of course, starting the thorium fusion cycle. This is a 2-grid system. One shows the jet approach, a jet actually happening there in the experiment, in the lab, existing, running, and in that case, you use it as a thruster for NASA. And this is a star plasma node. This is where you start using it as a neutron source. Another picture of the grids. The D plus D fusion reaction, of course, produces 1 neutron. If you think about using deuterium, you would like to think about what's called the catalyzed Dt reaction. It produces 1 neutron from the DD neutron branch and from the DT tritium branch, and that would be one of the choices. What we venture doing is a complete material and energy balance, the same approach as done by Lawson for pure fusion, where we consider a fusion core, one of those experiments, having a certain amplification of the plasma, giving out some energy from fusion. We talk about a direct converter if you have charged particles. We have a thermal conversion cycle if you use different, of course, fuels or coolants. In that case, we used really molten salts. We have a blanket that can breed uranium. It has a multiplication factor. Then the materials go to the fission satellites that themselves produce energy. And what matters for us, of course, is the different situation. If we use, say, DT, then we need a molten salt that must contain some lithium. And this is what's called the FLIBE, the lithium, thorium, fluorine, beryllium molten salt. If you don't use the DT and you don't need to breed tritium, you can substitute that lithium with sodium. And these were calculations done at the Oak Ridge National Laboratory, detailed neutronic calculations that calculated how much energy is produced by the neutrons, how much energy produced by the gamma rays, how much breeding occurs in the thorium-232, turning it into uranium-233. And the numbers in the energy balance you can read in the full paper gives me an important parameter here. Energy amplification in the system. Remember that the problem with fusion today is energy break-even. There isn't enough amplification of the plasma to provide us with net energy output. Now, suppose that we have a hybrid. The energy multiplication factor is now the energy that's produced by the total system divided by the energy produced by fusion. So you find that you have that factor of the energy released by fission divided by the energy produced by fusion.
And the energy produced by fission is interesting. Like a fission event produces for us, say, around 200 million electron volt, exactly 180. Let's say 200 million electron volt. And the energy produced, say, from the DT reaction is only 17.6. Let's say 20. So we have a factor of 200 divided by 10. We immediately get the benefit of a factor of 10 amplification for fusion. It gets us one step closer to really fusion breaking even. But that's not all. You find that we have another important factor here, that 1 minus C. What is that 1 minus C in the derivation? 1 minus C here is a conversion ratio that we get in the fission reactors. And it comes in from the summation of the breezing process. C is the average number of fissile nuclides produced divided by the average number of fissile nuclides consumed. If it is less than 1, we call it the conversion ratio. Existing light water reactors have a conversion ratio of 0.55. Advanced converters like the CANDU reactor in Canada has more like a factor of 0.9. Only if you start getting that factor of C larger than unity, then you call it breeding. But that factor of 1 minus C here in the denominator is fascinating because get me that factor to be just 0.5. Like existing light water reactors, 1 minus 0.5 is, of course, 0.5. So it gives you an amplification factor of 2. And if your C here is designed in the fission reactor to approach 1, the limit of that support ratio, or the energies that you can produce in your fission reactors relative to the fission, the energy that you have in your fusion reactor, notice 1 minus C at C tends to 1 is a factor divided by 0. And that means infinity, meaning that you can really multiply the energy in your existing fusion experiments that are not producing net energy by a factor of up to infinity. So it's really the goal of Professor Blanchard, for instance, to design reactors with different values of our C right there. That C comes in from the fact that as you start with, say, 1 uranium nucleus of 233, each one of them can breed by an extra neutron another uranium-233 nucleus, and that is a sum to infinity. Obviously, the engineers will tell us that we cannot really recycle an infinite number of times, so you can really substitute for that equation one that considers only n number of recycles and consider the equation valid. Notice here that these are the parameter values for the parametric studies that our young engineer is considering to identify really the ranges of operation. We took the plasma power amplification factor here as we asked the people running those experiments, how much is your power amplification factor? Tell us, oh, sorry, it's only 0.01, 1%. So as we learn more about fusion and we increase that power amplification factor, and as we design systems that have a conversion ratio of larger than 0.6, and we know that with the thorium cycle we can get close to 1 and even larger than 1, then basically we can think about an infinite power supply. Cost. Large machines, of course, like the ITER, the International Tokamak experiment, is costing us in the billions of dollars. Billions, all right? And the costs of this machine tends to scale as the cube of the system size and as the square of the strength of the magnetic field. That's for magnetic fusion, not inertial confinement fusion. So those full-scale machines really cost in the range of $180 to $200 million. If we go to the experiment that the Navy supported Bussard, and you can go and find some of Bussard papers in the references and inspect them, they basically paid him about $18 million over about a 10-year period. So that was about $1.8 million per year. Think about how many engineers and scientists in our national labs, universities, can start looking at those small experiments, improve on them, innovate, and create new ideas rather than
putting all our eggs in one basket in one single experiment as ITER. In general, then, I suggest that the use of diode, or which is electrostatic inertial confinement, or cusp magnetic fields, which you would call electromagnetic confinement, experiments that right now are only neutron producers or, at best, ion thrusters for space probes, can be used as neutron sources. Of course, Fermilab can tell us also about their ideas about using particle accelerators can also be used as neutron sources. Coupling of fusion-fission thorium hybrid gets us close both to the future of a pure fusion system and introducing the thorium fuel cycle. Obviously, everybody agrees that our uranium-plutonium fuel cycle is doomed for many reasons that could be another talk by itself. A configuration where you couple fusion and fission allows enough energy break-even for a sustainable energy system with, we can say it, with breeding, unlimited fuel supply base, both from the availability of thorium in the Earth's crust, 4 times that of uranium, as well as that deuterium that composes really the Earth. The Earth is, of course, a water planet in general. And eventually, if we improve on those small experiments from fusion, we may eventually get fusion cycles such as we get pure fusion, what Bussard's dream has been, the proton-boron 11 cycle, producing pure fusion without radioactivity. And, of course, if you produce only charged particles, this is the best kind of a rocket that can get us beyond the confines of even the solar system in general. So it's really a situation that needs to be considered when we talk about fusion and the coupling with fission, is that fission helps fusion really increase its energy break-even, and at the same time, fusion could help the thorium cycle by providing it with the source of neutrons that it needs to get started up. And we are trying to put the system into equations that are irrecoverable when you plug in the right numbers. I'd appreciate it if you review our equations. Any corrections would be appreciated. And thank you so much for your attention.